Welcome to lecture 39 of Industrial Mathematics and Computation. So this is the third lecture on machine learning, although I hope it can be made as much as possible self-contained. So we will introduce in particular deep learning. Um, we do the learning today with Flux, a Julia package. We actually have three examples. Our first example comes from the getting started with Flux. It's a very basic example. The second equation we have covered in our previous lecture, but then with a very self-contained Julia implementation. Here we consider that example again, but now we will train it and model it with Flux. And then we arrive at very interesting application or illustration, the application of a neural network to recognize handwritten numbers. So I've heard this example being described as the hello world in machine learning. Okay, so let's first recall some definitions. So, what is machine learning? One could say it's indistinguishable from statistics, but as a computer scientist, we can work with the following definition here. So, it is a way of programming without without much coding, essentially. So, we are aiming to perform certain tasks, and the tasks will and we have a performance metric for those tasks. As we are gaining more and more experience in executing these tasks, the performance will also improve. So the way of programming, of improving the performance on a class of tasks given on experience can be defined as machine learning. Prior to making these lectures, I learned a lot from scikit-learn. So my knowledge has since then improved, mainly through the Julia experience. Okay, so what is a neural network again? Well, a neural network is a composition of nonlinear functions of two or more neurons, where a neuron is a nonlinear bounded function depending on some inputs. So here we have n variables in this formulation, and we have p parameters, or also called weights. So then what is deep learning? So deep learning is working with a neural network that has multiple layers. So I took this picture from recommended source. So this is a set of lecture notes that is freely available. The URL is at the bottom. What does this picture indicate? The green disks consist of the inputs, the red ones are the outputs of the neural network, and in between are the blue neurons in the hidden layers, in the multiple layers. So this is a neural network that consists of 7 layers. Okay, so let's start our first example. So first of all, what is Flux? Flux is a machine learning library that comes for free. So if you are in a Julia session, you type in using Flux, then it will download it for you and add it to the packages that you have already installed. There is a paper that describes Flux. You see this is a multi-authored effort. In this first steps with Flux, I will go through an example step by step. So the first steps are typically the hardest. So the first step is always to understand what is actually the task, what is the problem that you want to solve. Then what are the data and in which format should you present the data? So that's the second step. Then there is the definition and the initialization of the model. These are the first three important steps. And once you get through that, then it tends to go more or less automatically because Flux will give you additional support for loss functions for optimizers. And also in training the model is typically only a couple of instructions. So I will repeat this step-by-step process for this example and also for the two other examples that we will consider. Alright, so what is our task? So we consider a function depending on 5 input variables. There are 5 input variables. I'm sorry, shouldn't use the term parameters. So the parameters are the weights and then the bias numbers. So we have a matrix, 2 rows, 5 columns. So from the columns we see that the x must be a vector of 5 numbers. There is one bias vector. The number of rows in the weights matrix must correspond to the number of elements in the bias vector. Okay, so that's the formal setup in this very simple task. We can see this as an approximation problem. So we have an exact function here. So we are in the context of supervised learning. So we have an exact weight matrix or a true weight matrix and a true bias vector. So if we are evaluating this model at random data or at some given set of data, can we recover the weight matrix and the basis vector from those observations? So the observations are called training data. So this is the task that we have to solve. Recover the weights and the bias vector from the training data. Okay, step 2. What is the training data now? Well, we have every time when we look at our model, we will have to feed it 5 numbers. And on return, we will have 2 numbers. So the input consists of 5 numbers, the output of 2 numbers. Here I've tried to formalize this. So the ith vector is a column in a matrix where we take numbers that are centered at 5 and uniformly distributed. So there, sometimes we subtract at most 1, sometimes we add at most 1. So the UJIs are random numbers uniformly drawn from the standard uniform distribution from the interval 0, 1. For the output, we took still the output of the inputs. So in some sense, if I would keep, so the x's are at random, but somehow to be more realistic, we also kind of change the output. So this is seldomly when we observe data, it's seldomly that we have it exact. So this is where statistics, by the way, comes in again. So we have now the outputs. So here the intermediate letters, the ZIs, are when we evaluate the random x vectors at our exact function. So we take those two numbers and we add random numbers to it, but now the random numbers are normally distributed, following the standard Gaussian with mean 0 and standard deviation 0.2. So it's not standard after we multiply with 0.2. Okay, so n is the size of the training set, and that's often a very important decision that we also make here. How large is our training set? Pick it too small and it's not representative enough. Pick it too large and training your model will take a very, very long time. You also risk the overfitting problem, where your model is very accurate on the training data, but is not really useful on the testing data. So that's the problem of overfitting by choosing your training set too large. Okay, step 3. Step 3 is typically also a difficult step. How many layers in the network to use, but now it's actually a very simple model. We will also use a 2x5 weight matrix and 2 vector for the bias vector. So our model is actually exactly the same as the given function. We are doing supervised learning and we are setting up our own problem. So in defining the model, it's a very important decision what are the sizes of the networks, how many layers you are going to use. So here it is a 1-layer network. Okay, then steps 4, 5, and 6. So there's a typo here, it should be step 4. Steps 4, 5, and 6 are so small that I just put them all on one slide. So the loss function determines the performance. So the performance, remember the definition of machine learning, we have to measure, we have to compare the observed data or the exact data in our example here, or the given labels, to the labels that are produced by the model. So the model is initialized with random weight matrix and random bias. So in this loss function here, we take the difference, the component-wise difference, and we raise this to the power 2 and add this up. So there is the learning rate, so we use the classical gradient descent. And then the training of the model is happening by one single instructions. We pass the loss function, the parameters. So if we have W and B, the params function will actually extract the parameters from this. Not that this is difficult here. The training data are the zipped x vectors and y vectors, and the optimizer is the optimizer defined in step 5. Alright, there is a variation of this. We can do this the longer way. Here, the longer way allows me also to specify in greater detail the selection of the optimizer with the learning rate 0.01. The longer way looks more confusing and cumbersome, but it has the advantage that in every step we will really see the evolution of the loss function. So when we do loss xy here, we can assign this to some entry in a vector that also then is of size n. So here we are going to run, so the capital N, the number of training steps that we are doing is here implicit. We are taking the entire training set x and y and we run to all the tuples. Okay, so first exercise, run this and make a plot of the loss function. So we are doing here 10,000 steps. Is this really necessary? Okay, so I'm skipping some steps here. So there is a Jupyter notebook posted. So please take a look at this, especially if you want to do the exercise. So let's go to a more larger example. And I will take the example that we considered last time. So the last time we had the reference, so I looked in the last lecture, we considered part of this paper, and by bringing up this paper again, I would strongly encourage you to read the rest of the paper. It also allows me to again refresh the definition. So what is a neural network? Here we have a neural network with 3 layers. So the input layer gets passed to the first layer. So we have 2 inputs and 2 neurons and the second layer. So the weight matrix at that level will be a 2 by 2. The bias vector will also be a 2 vector. We go from a 2 layer to a 3 layer with 3 neurons. So the weight matrix here will be a 3 by 2 matrix. So W3 will be a 3 by 2 matrix. The bias vector will be a 3 vector. So then in the last layer we go to the outputs. So we have 2 outputs here, and that means that our weight matrix will be a 2 by 3. So takes in 3 inputs from the previous layer and gives 2 outputs. Also the bias vector at the third level is a 2 vector. So what is important is that from this picture you can deduce the total number of parameters. Okay, so what is our problem now? We have a set of points, coordinates given here in the plane for x1 ranging from 0 to 1, x2 also ranging from 0 to 1. So here you see our bottommost leftmost point, which is labeled as a success. The red points are labeled as failure. So what is the problem now? The problem is that we can build a function of points, values for the first and the second coordinate, and that will return a success or failure based on this pattern. So for any point in the plane, we want to be able to classify the points either as blue or red. Here is the numerical data. So our bottommost leftmost point was 0, 1, 0, 1. It was colored blue, so the label that comes with this, so the output is also a 2 vector. So if it is a success, then the first component will be 1, the second component will be 0. So the first 5 points were the blue points on the previous slide. The last 5 points are the red points. So now again, what is the task? I should probably have said task instead of problem. Find now a function so that the labels are corresponding to the labels given for those 10 training points for any point actually. And what we will do is so this seems like an exact problem, a binary problem. It's either 1, 0 or 0, 1. But in our model, we will have 2 numbers, y1 and y2, and we will label, so there will be a binary classification. A point will be labeled a success when its y1 value is larger than the y2 value. Okay, we went very carefully through this example last time. So last time that was our only example. Here we will solve this example with flux. I indicated on the previous time that this picture came up that we can read off the dimensions of the parameters. So here are they. With flux, we can define random. We can, if we can provide the input dimension, saying that the first layer takes on input two vectors and produces two vectors. So that is the case here. We can just specify the dimensions. In that case, Flux will generate random matrices, but we can also provide our own matrices. This has the advantage here if you want to compare with the pure Julia solving that we did in the last lecture, then you use the same random matrices. We can, so in our first getting started, we just had the model was w times x plus b. Here the wx plus b gets given on input to the sigmoid function. So a sigmoid is a smoothed step function. Okay, so defining one layer in Flux is just one instruction, and then with chain we link these three layers into a network or a model M. Okay, so here you see the output. So when you make the chain, for every layer it indicates the number of parameters. And here you see essentially the first exercise of the previous lecture solved. So this problem has 23 parameters. So I'm giving here the sigmoid as slash sigma, but if you run this, you will see the actual Greek symbol appearing. In my layout, this was not so much possible. Okay, so let's now go through the process to train the network. We have already our data that was given to us. We have the labels, we have the model. So in a way we have done already the three steps. Now we are step 4, defining the loss function. Here it's great that we've done the previous lecture, so I'm using the same loss function that we coded up. The loss function depends on an x and a y value, although we take the training data. So we have 10 points from the training data, and we see how well at those 10 training points the model does. So essentially we evaluate this formula here. So we have the given labels stored in that 2 by 10 matrix. So here you see the selection. So the matrix is called Y labels. So the points are stored in the column. So the I runs over the columns in the matrix. We evaluate the point, the ith point, the ith training point at the data. So that gives us the YY, and the YY is here what we called, what was indicated in the first step, the Y hat. So here you see that this is the model, the output of the model. Okay, then we train. So here we do this with 1 million points. Calling the descent method with learning rate 0.01. Now this takes a while, and one can also ask, why do you really need 1 million points? That's the question that I'm going to ask you in the exercises. So here we have two pictures. So we have this picture when I ran the code of last time. Here you see the code with flux. So there is some changes there. So this is not an exact problem. If I flip back and forth, you can see the small differences between the plots. The outcome here with the code of the pure Julia code, and here with the uh, train of flux. So the successful points, the 5 successful points, are now indicated in white. Everything that is surrounding in blue is computed. So these are points where the first output was larger than the second output. The unsuccessful points, the unsuccessful training data, are given by the black dots, and everything that is in red is computed by evaluating the model. So the outcome of this training is that we can label every point in the region of interest. So for x1 going from 0 to 1, x2 going from 0 to 1, every point can be classified either a success or a failure. Note that this is not an exact problem. With another optimizer, we might have found a different solution. So you see that there are differences at the edges. Okay, so do we really need 1 million points? And actually observe that flux takes a little bit longer. What we did in the last lecture, we were actually clever, or the paper was suggesting a clever solution that we would pick a random training point. Here we go through all the training points, so it may very well be that we do at least 10 times more work with flux than we did in the previous solving. We had a long way to run the training. Do this also here and plot the loss function. First for 1 million. And then from the shape of the loss function, you will see that can you, for example, cut the number of training steps in half or not. Choosing the training points, we are working with the given data, so with the labeled data, we are in the 0, 1 region, but I was using normally distributed numbers, and that's actually with mean 0 and standard deviation 1. So in some sense, I was only using one quadrant of all the generated points. Perhaps that's not a very good way to work. So see if you get better results if you would use all your generated points would be in the first quadrant in the unit square. Also relate this to the loss function, the evolution of the loss function. Okay, so now when I started machine learning, I came up with pictures, but then we didn't return to the pictures. Here, this is to make good. So there is the classic image classification dataset, which is used all over. So you will find it in also other part of other training sets, not only Julia, I suppose, not only Flux. But we are downloading it here through the package management system from Julia. So there is an MNIST entry in the ML datasets. When I was preparing this, I checked the documentation of Flux first, also the deep learning notes. But actually, what was most helpful here was this post at the bottom. So there is a lot of useful information out there. You may have to be a little bit persistent in finding what the best approach is to solve the problem. Okay, what is the problem now? Here is one of these images. So the data set comes with some utilities. One of the utilities will convert the matrix, the input matrix, to a colorant array. So here you see the pixelated, so this is a 28 by 28 matrix, where some of the dots were in black and what was written is in white, and then there are the edges that are smudged with gray. So the input is essentially a numerical matrix. We will recognize this as kind of the number 5. Here it's perhaps a little bit clearer. So the first 5 images can be interpreted as a zip code. So this could be an application for this neural network. Recognize the handwritten letters that are on an envelope. The handwritten numbers, I'm sorry. So I'm sure that there are also databases for letters, but here we restrict to numbers. So these images are available when you download this data set in Train Tensor, and then also in Train Labels. So the label for the first image will be 5, for the second label will be 0, then third one 4, then 1 and 9. So this is again an example of supervised training. So for the entire set of 70,000 images, we know the correct answer. The task is now to recognize or to train a network that recognizes those images correctly. All right, I will go through the 6-step stage. They're a little bit more involved than what we've seen before, and I might not be able to explain everything all that well. So we have the labels. The output labels are just numbers, but in the multi-classification problem, or the multi-classification task, we map every number into a vector. It's similar to our artificial network. We had success and failure, and that was mapped into a 2-vector. Here we map the number into a vector. So every label, so if the number is 5, then every entry in this vector here starts at 0. So we have 5 zeros. That's essentially saying that the number is not 0, not 1, not 2, not 3, not 4. So I have 5 trials, but it is a 5. So every label is mapped into a vector. So that's what the one-hot patch does. It creates these vectors of size 10. All right, then how do we deal with the images? And actually, most important, what is the size of your training data? I made the mistakes to first do this with the entire training set, 70,000, and then the conversion took already an enormous amount of time. So the conversion here is done the long way because I had to practice this myself. So we do 2 steps in the conversion. So there is a colorant image with the 1 byte types corresponding to the grayscale. But the 28 by 28 should be mapped first to a vector. So we initialize a matrix of images. So the columns of the matrix images, every column will consist of 1 matrix. And we use as training data the first 100 images. So we loop through these 100 images. We with reshape we turn the images into vectors, and then the data types that are in each vector are converted into floats. So then these vectors here are stored in the columns of the images. So the images being a matrix of floating point numbers now. Okay, first decide on the size of your training set, and this is now shown as a one-step process, but the 100 might not be the best value. I picked 100 because it's a nice number, and actually it worked out. But for some applications, more will be needed. But you can also take too many, which by then you overfit your model. Okay, so then defining the model. So now you see this is already a model that is a lot larger. So we have on input a vector of 784 numbers. That's 28 by 28. So this maps to 40 neurons and then maps to 10 neurons. And then we have the third layer that maps everything again to this 10 multi-classification vector. So the vector of 10 numbers. So this formulates what is called logistic regression. So in the reference that I mentioned, the deep learning notes with Flux, it starts at chapter 7 with the definition of the sigmoids, but it also goes a little bit into greater detail in the description of the components that can be used. So in the artificial network, we use sigmoids. An alternative to a step function is kind of using a ramp function, a rectified linear output. So this is not as much a sigmoid, but it's more a linear function where you can still, with the weights, you can still adjust the slopes and you can still shift them with the bias. Okay, now you see that we have more than 30,000 parameters. So it's still relatively, for actual applications, it's a relatively small model, but still it's considerably larger than our first artificial network. Okay, so this is a network with 3 layers. And we can check it. So here, so one shouldn't wait till the very end. If something is wrong with the model, you can check this already here. So we have our training set of 100 images. So if there would be something wrong here with the input dimension, which should be 784, which is the length of the vectors, or if the type would not be good. So there are many things that can go wrong. 2 problems are that the dimensions in network are not matching the dimensions of the images. It could also be, for example, that the images are of the wrong type. So we expect floating point numbers on input. So if one evaluates this, then one obtains one vector. And here the network is not yet trained. It is initialized with random matrices for the weights and the bias vectors. So here we will not see that this 10th image is correctly classified. So we would not expect this. Okay, I'm almost 40 minutes in, but the problem is actually almost solved because now Flux is taking over. Well, here we are already relying on Flux, but now steps 4 and 5 are actually quite straightforward. So and I'm sure that I cannot explain everything. So for the optimizer, we touched on the gradient descent methods with algorithmic differentiation last time. So in the deep learning nodes, this is specified, described in greater detail. Here in step 5, we select an adaptive gradient descent method. For the loss function, there is this cross entropy, which is quite appropriate when we are working with this multiple classes classifications. So we have 10 classes where we want to classify our images. Then the cross entropy is quite appropriate to use. So in some sense, Flux takes away a lot of complexity here. And then in the training of the model, we are defining a callback function. In a way, this is a more sophisticated solution. So I copied this from the post that was earlier mentioned. So we have the loss function that we report. The progress is a function that is called when we train the model. Here you see the CB for callback, and we will call this callback function every 10 seconds. So this is quite convenient because the training, essentially it's a black box and we don't really know what is happening. And it could be that it takes a very long time and we don't know the progress. So there is the longer way of running it, running the training, as I illustrated before. Here it's a more advanced form of running a little bit the longer way, except that we here work with the callback function. We can also define what is called the number of epochs. An epoch is one entire cycle where we cycle through the data, through the entire training data. So we will cycle 100 times to train this network. And it turns out that if you look to the output of the callback function, then that output is quite regular. Perhaps I should have shown the Jupyter notebook. And perhaps I can still do this. Let me move to the next last slide, essentially. So verification. So this is not really a step, but whenever you compute something, you should be able to sense what the meaning is of this example now. So if we take the first 5 images, or here I take the first image, and I evaluate this, then you will see that you will get 10 numbers back. And then, perhaps I should have shown now the output. And then what you will essentially see is that the number, which is now at the 6th position, will be actually the largest. It will not be exactly 1, it will be 0.9 something, but that corresponds to the encoding of the label in the vector of size then. So the first 5 images are verified and they are classified correctly, and you can also do this with the rest of the training data. You can go systematically through all 100 of them, but you can also take a random sample, as is done here. The last exercise is to verify for one of the remaining 70,000 minus 100 images. You can do this also at random. Here the difficulty is that you still have to do the conversion. So the images are, when you go to the trained tensor, the images are stored as 28 by 28 matrices where the data types are bytes. So you must convert to use this model as one single vector of floating point numbers. So this 4th exercise is an invitation to run the Jupyter Notebook. And then see them, I'm trying not to run over time, so I will not show the Jupyter Notebook, but please by all means check the Jupyter Notebook that is posted at the course website. So here are the most important references. Um, so there is the Flux package that we have been using in Julia. There is the Deep Learning for Applied Mathematicians, the SIME review paper. So this is a math course as well. It's an industrial math course, but SIME is quite important. The I in SIME stands for industrial. Then you see more background. You can read more background from these deep learning notes here. And in particular, again, machine learning can be seen as an extension of statistics. So you will see when you read, when you go through those notes, that there's a lot more background that we tried to touch on also last time. Okay, so I thank you for watching this recording. I hope this was useful.